As this applies to error analysis, the differential can be used to easily approximate errors in a function of more than one variable based on errors in each of the independent variables. This is useful for engineers when precision of measurements is crucial.
Ooh.
So if we're making a cylindrical, right, circular, cans, right, for a company, and the cans are 4 inches high with a radius of 1 inch, but these dimensions are only accurate in height to the nearest 1/10 of an inch, and in the radius to the nearest 5/100ths of an inch. What's the possible amount of propagated error in the volume of the can? Forgive the non-metric units. And what is the percent error of the volume? Well, you know, the amount that it's off in height is only 1/10 of an inch, and the radius off by 5/100ths of an inch. Doesn't seem like it's going to be off by a very high percent. This might be a very surprising problem. Of course, the total differential, we can find that as we did in the 2 preceding examples. So dz is 2 pi times x times y dx, because that's the derivative of this with respect to x times dx, the differential with respect to x, and then the partial derivative of this with respect to y, which is just pi x squared times dy. So we got our total differential. Well, we actually got that in the last problem. And so dz is 2 pi times x, which is, recall, 1, times y, which is, recall, 4, times 0.05, and recall dx is the error amount in the radius. This is pi radius squared times the height. So, and then filling in pi times the radius squared, well, that's still 1 squared, times the error in the height, which is 1/10. Right? So if I multiplied all this out, I do indeed get, looks like 0.5, plus or minus 0.5 pi, so call it pi over 2 if you wish, right? So the dz, the total differential, the total amount of error that could be in the can would be plus or minus pi over 2 cubic inches. Doesn't seem like a big error, but the question is, what is the percent error of volume? Remember, like, as a percent, we were only off in the height by what, 0.1 over 4? That would be, well, 1/10 of 1/4, about 1/40th. So that's about 2.5% error in the height. And then the radius, our error is, well, like 1/20th of 1 inch. So call that, I said 1/40th. Did I say 2.5% in the height and off by 5% in the radius? That's not much. But here's the surprise. If we go to look at the percent error, we'd have to see what fraction of the volume this error amount is. And so the volume, I approximated it at 12.56, or 12.566, I guess, but really, if you evaluated this function, f of 1,4, it's pi times 1 squared times 4, so it's 4 pi. Maybe that would be a better thing to say here, 4 pi. And so pi over 2 divided by 4 pi, which is really what our error amount is. It is pi over 2 divided by 4 pi. As an approximation, the pi's would cancel, and I think you can see that simplifies to 1/8. Well, that means our error amount could be 1/8 of the volume of the can. Our little teeny errors, if you recall, what we say, 2.5% on the height and 5% on the area, or I'm sorry, on the radius, gives us a possible error of 12.5% when we calculate the volume. So now you see why it's called error propagation.